Hey folks, this is the second video in section 7.6 dealing with solving trig equations. Let's go all the way down to example 5. Example 5 starts with what I call the weird examples. So the first 4 examples were just kind of run-of-the-mill, very normal, common examples that you're going to see frequently. Example 5 starts a whole section of what I call the weird examples. So you see here, I've even written a little note that these are kind of rare, but you might run into them in their study plan or on your quizzes. So you do need to know how to do these. Now, every once in a while, what you're going to see is that it would be helpful if I could square both sides. And that's the case here. How do you know to do that? Well, quite frankly, we're told to. And again, this is rare. You're not going to see this a whole lot, but it is going to happen occasionally. So let's take a look at what we should do. Notice that the first thing we're going to do is we're going to square both sides. In order to square the left, I need to use foiling. I did not show my work on foiling. I just simply foiled and wrote down my trinomial after I foil. So understand I did foil there, first, outer, inner, last. And I also squared the right side of the equal sign as well. All right, so then the next thing that I can do is there's no like terms that I can combine. However, we know that cosecant squared is the same thing as 1 plus cotangent squared. If I can change this into 1 plus cotangent squared, I will have all the same trigonometric function that I'm working with. So using my Pythagorean identity, then I will change cosecant squared into 1 plus cotangent squared. Now, take a look at what I've done. I've already didn't show my work or talk through it, but I've already done this. I subtracted cotangent squared on both sides so that this cotangent squared and this cotangent squared ended up zeroing each other out. That is totally legal, so no problems there. So now let's combine our like terms for the rest. That'll be negative 2 root 3 cotangent is equal to negative 2. Let's go ahead and divide both sides by negative 2 root 3. And so this is going to turn into root 3 over 3. Okay, so then we go to the unit circle and we ask ourselves, where is cotangent equal to root 3 over 3? Well, the first thing that my brain says is that cotangent is positive in quadrants 1 and 3. Notice in our instructions, we are dealing in radians, so keep your thoughts on that. And so where then in quadrants 1 and 3 does cotangent equal to root 3 over 3? Basically, I want a cosine value that's a half. So that is going to occur here at pi over 3 and down here at 4 pi over 3. So pi over 3 and 4 pi over 3. Now, we would love to say, hey, we're done, but unfortunately we're not. Do you remember how in the last video I talked to you about if you were to divide on both sides by a trig function, you would lose solutions? Well, the opposite is also true. Notice that we squared on both sides, and this actually gives us extra solutions. So anytime you square on both sides, you need to check your work to see if there's any extra solutions. And if there are extra solutions, we have to throw them out. So I need to take both of my solutions. I'm going to plug them into the original equation without the squaring, and I'm going to see if they work. If they don't work, I need to throw it out. All right, so let's test out the pi over 3 first. So cotangent pi over 3 minus root 3. Again, all I'm doing is plugging into the equation is equal to cosecant pi over 3. Cotangent pi over 3 is root 3 over 3 minus root 3 is equal to the cosecant of pi over 3 is 2 over root 3. I'm just using unit circle values here, folks. Not a whole lot of math going on other than just using my unit circle. I did this in here is I'm getting a common denominator so that I can subtract these two. So my common denominator is a 3, so I'm just multiplying by a 3 over 3. So my common denominator then is a 3 on bottom. My numerator here is root 3, and my new numerator here is a negative 3 root 3. Root 3 minus 3 root 3, literally you could say it's 1 root 3 minus 3 root 3 is going to give you a negative 2 root 3. You'll notice that negative 2 root 3 and a positive well, I didn't finish that up, but even still, a negative and a positive are never going to equal each other. So pi over 3 is a value that needs to be thrown out. Now let's go and check the 4 pi over 3 and see if it does the same thing. So once again, let's plug it into that original equation. Cotangent 4 pi, excuse me, over 3 is root 3 over 3 minus root 3, and the cosecant on the right side is negative 2 over root 3. So this time we have negative 2 root 3 over 3 and negative 2 root 3 over 3 on both sides. So these are equal to each other. So 4 pi over 3 is a solution that I can keep. So once again, if you decide to square both sides, it's rare, but if you decide to do that, make sure at the end that you check for any extra solutions. It's highly possible that you will have extra solutions. All right, so when you're solving a trig equation, this little gray box here is basically just sort of a an overview of what we've already done in the videos. And so basically, is the equation linear or is it quadratic? Number 2, if there's only one trig function present, then solve it for that function. After that, you can solve for the theta or the angle. Number 3, if more than one trig function is present, rewrite so that one side equals 0. Then you can either use factoring and applying the zero product property, or you can use the quadratic formula if it's not factorable. Make sure that you check your solutions. And number 5, you can try using identities, and then sometimes it's helpful to square both sides. Just in this case, make sure that you check for extra solutions. And I just wrote a little note here, just like that I already mentioned verbally a few moments ago. All right, example number 6. So again, we're continuing on with some of the what I call the weird examples. So in this case, we're looking at working with a half angle. So the equation that we have is this right here. I only have a single trig function. Let's isolate this trig function, and then I'll worry about isolating the x value. So the first thing that we'll do is just add root 2 and divide by 2 on both sides. And then what I'm going to do is just pretend that this is a theta or some other variable, an alpha or something. Cosine of some angle is equal to root 2 over 2. Where does cosine equal root 2 over 2? And we know that it's going to occur either in quadrant 1 or 4, and it's going to occur smack dab in the middle. We're working in radians, so this is going to be pi over 4 or 7 pi over 4. So x over 2, my angle is going to equal pi over 4, or my angle is going to equal 7 pi over 4. And once I have it set up like this, all I have to do is multiply both sides by 2 so that I can isolate the x. So that will be x is equal to 2 pi over 4, which is the same thing as pi over 2. Or x is equal to 14 pi over 4, which is the same thing as 7 pi over 2. I wanted to mention that there is an alternate way that you could have solved this one by thinking back to what you learned in graphing. So really quickly, again, this is the equation that we have. If you think about this as if you had to graph it, my amplitude here would be 2. My period would, now this one's a little bit tricky, my period would be 2 pi over 1/2 because my b value is 1/2. And so this would be 2 pi over 1/2. When I simplify that, that's 4 pi. I don't have any kind of a phase shift, and my vertical shift is to go down square root of 2. I went ahead and graphed this. You can take the time to graph if you want to. And you'll notice here that my interval was from 0 to pi over 2. So I want to know, where does this guy equal 0? Literally, where does this guy cross over the x-axis between 0 and 2 pi? Well, here's 0 and here's 2 pi. It only crosses over the x-axis one time. This one is not in my interval, so I need to throw this guy out because it does not meet the restriction that I was handed. So that's just an alternative method of using something that you've already learned to solve. All right, equations with multiple angles. Example number 7, using a double angle identity. So you notice here we've got a double angle, And so I can use one of my identities to substitute for cosine double angle. All right, so I am going to use, I'm going to use the one that has signs in it because I already had a sign on the other side. So cosine double angle is the same thing as 1 minus 2 sine squared. I went ahead and took this one over to the left side. So that's minus sine of x is equal to 0. And this looks like one of my normal quadratics. So what I did was I basically took all three pieces to the other side. That's a psychological issue for me. I like having a positive a value personally. All right, so it is factorable. So I went ahead and used the zero product property, the zero factor property to set up two miniature equations. And then I'll solve each of those mini equations. So that first one is going to be sine is equal to 1/2. Sine is equal to 1/2 here and here. Let's look at the directions. I'm working in radians. That's going to be at pi over 6 and 5 pi over 6. And then on the other one, sine is going to equal a -1. Sine equals a -1 down at the bottom, which is going to be at 3 pi over 2. So I have three solutions then for x. All right, example number 8. Again, this is one of those that's kind of rare. You won't see too many of these, but it is possible that you might see it in the study plan or on your quizzes, so it's good to know. All right, so for part A, I am working in degrees. All right, so the first thing that I notice, and I am given this hint of working with a double angle identity, I notice that I have this cosine squared minus sine squared. Unfortunately, I have these 2's in there. So just in these two terms, I have a GCF of 2. So what I chose to do was to factor out the 2 just out of those two terms. And then what I could do on the inside is I could use my double angle identity and turn this into a cosine double angle. So that was what I did next, cosine double angle. And now I only have one single trig function, so I can isolate that one single trig function by subtracting 1 and dividing by 2. So we have cosine double angle is equal to a -1/2. And now here's the thing. Where does cosine of some angle equal a -1/2? Well, cosine is equal to a -1/2 at, let's say I'm working in degrees, at 120 degrees and at, sorry about that, 240 degrees. My mind blanked there for just a moment. 240 degrees. So either my double angle is going to be 120 degrees or my double angle is going to be 240 degrees. Now, so far, everything's totally normal. Let's go ahead and isolate theta by dividing by 2 on both sides, and I have a theta of 60 and a theta of 120 degrees. Now, here's where it gets weird. Here's where we often don't think to go any further. Because we were working with a single theta, but then we turned it into a double theta, that's where we need to realize that we're being prompted to go a little bit of extra here. All right, so what I'm going to do, since this is double thetas, I'm going to go around the circle a second time. So this is 120 degrees. If I went around the circle another time by adding 360, that would land me at 480. Now, 480 degrees is totally outside of our restriction. However, this is double angle. If I divide by 2, I'm going to get 240 degrees for my single theta, and my single theta is within my restriction. So if I don't go around again, I'm actually going to forget some of my solutions. Let's do that with this one as well. This one was at 240 degrees. Let's add a whole circle to that. Add a 360 to that. Yes, that's outside of my range, 600 degrees, but if I divide by 2 on both sides, that's going to give me 300, and 300 is within my restriction. So I have 4 solutions. All 4 are highlighted for this particular example. All right, I think that's the last example. So that is the end of this particular video.